So far, we have looked at logarithms and we have used logarithms to the base of 10. So we always used log 10 of, say, a number, let's call it A, something like that. And this actually came from us saying, right, we have 10 to the power of x equals a, and we wanted to find this x, and therefore what we did was we took both sides log 10, so we took log 10 of 10 to the power of x equals log 10 of the number of the value a. And we said this log 10 and 10 cancels out, and therefore we've got x equals log 10 of a. And then we did some calculations and we applied some of the rules, for example, the multiplication and the division rule or the power rule. And we were able to use these operations to calculate x, for example. Now, of course, there is no rule in the entire universe that we always have to use the base of 10. Probably for most of us, 10 is, say, something that we are used to, a decimal system, and I guess this is probably because we've got 10 fingers and we are used to, or we were used to, use our fingers when we did some basic mathematical operations like addition or something like that. But imagine, for example, other aliens maybe who don't have 10 fingers, maybe they've got a different number of fingers. Actually, it's quite interesting because apparently the Inca in South America didn't use the decimal system, they used a system based on the number 12. And a lot of scientists were quite puzzled by that. Why do they use 12? And I remember reading somewhere that apparently at that time when they came up with this system, the king suffered from a very rare genetic mutation where he had, instead of 10 fingers, he had 12 fingers. So for him, the decimal system wouldn't have made sense because he could use 12 fingers, actually. Imagine how he must have played piano. That's absolutely fantastic. So we don't have to use something like 10. We can use any other base, so we could use 12. Sometimes when you are a computer person, you are familiar to the base 2. So we would, for example, have 2 to the power of x equals, let's say, 64. And this is really exactly similar to what we had before with the 10. So if I write that here, 10 to the power of x equals 1000. So we basically said, how often do we have to write times 10 to get 1000? So we said 10 times 10 times 10. So this would be 3 times, and that would give us 1000. So that would be 10 to the power of 3. And of course we can do the same thing with 2. So we can say 2 times 2 times 2 times 2. So that's 4 times 2. Let's see. 2 times 2 is 4. 8, 16, 32, and we need one more. So that would give us 64, and we can write 2 to the power of 1, 2, 3, 4, 5, 6. 2 to the power of 6 equals 64. And if we have 2 to the power of x equals 64, what we would do, following this formalism that we looked at here, we would just simply say we take both sides of the equation, log to the base of 2, not 10 as we had before, because 10 was our base here. Now we use 2 as our base, log 2. And what we get is log 2 of 2 to the power of x equals log 2 of 64. And what we see here is log 2 and 2, because we've got the 2 in both, cancel each other out, and we have left x equals log 2 of 64. And we've just done that, and we know that this would give us 6. In fact, we don't have to use 2. We can, as I said, we can use any other number. A very common number, actually, is a number that looks a little bit weird. That is 2.718, and it is a number with infinite digits. This is a very, very common number which we find a lot in nature, and I will do a video where this number actually comes from. It is a little bit like the number pi for a circle, where we have 3.1415, and it goes on and on and on. Now this number here, 2.718, and so on and so forth, this is commonly known as lowercase e, and it's in honor of the German mathematician Euler, spelled with EU at the beginning. So this is the Euler's number, and very often we use this 2.718 as a base. So we would have something like 2.718 to the power of x equals a certain number, a, which is then also written as a shorthand e to the power of x equals a. And if we just want to find x, what we need to do, like we've done here in this case, we just do the inverse mathematical operation. So we take both sides log e. And what we get from that is log e of e to the power of x equals log e of a. And because, and what we see here, log e and e cancels out, so what we have is x equals log e of a. And because this log e, people usually don't really like writing letters as a sort of subscript, and because it is so common, very often found in nature, it has its own symbol. It is ln, which stands for the logarithm naturalis, because it's so often in nature. So here we would write it as ln of a. X equals ln of a. And we can actually look at that there is even a key on the calculator. So let's say we have e to the power of x equals, let's say, 10. If we want to find x, and we remember this here is the base 2.718 and goes on and on and on. So if we want to find x in this case, we take both sides log of e, or as I said, we can just simply write ln and makes it shorter. So we do ln of e to the power of x equals ln of 10. And we remember, because this ln is the same as this log e, ln and e cancels out, so we've got x equals ln of 10. Let's see what this gives us when we go to our calculator. So here is the calculator, and we have a key actually, so we've got ln here, 10, close the brackets, and this gives us 2.303. Let's call it 2.303 to 3 decimal points. So x equals 2.303. So that's how we can actually use a different base, and in this case the base of e. Now, what about our rules that we said? Now, remember we said rule number 1 was log 10 of a times b, and we said that is log 10 of a plus log 10 of b. Now, do we have to learn new rules depending on what the base here is? And the good thing is, no, we don't. Absolutely not. We can now even write a general form where we have log, and we can call this any number, let's say log c of a times b, gives us log c, still the same number, is this c, times a plus log c of b. And the same thing, log c of a divided by b gives us log c of a minus log c of b. And likewise, log c of a to the power of b, that gives us b times log c of a. So we don't really need to learn any new numbers or new rules. What applied and worked for log 10, these rules also work for basically any base that we can think of, and the base doesn't really have to be even a whole number. It can be, like we have seen, 2.718. So this is quite convenient, and in the next video I will show you how we can actually convert these different bases, because if you look at the calculator that we have an ln, yes, we know what the base is, this is this e. We have log, which is usually log 10, but if we want to do something to the log of the base 2, so for computer stuff where you have everything in binary things, either 0 or 1, so everything is 2 to the power of something, we don't have log to the base of 2 on a calculator. And in the next video I show you how we can actually make a conversion into different bases. So stay tuned and thank you for watching.